So today I will emphasize the doubling method. You have already heard by the talk of Yolanta what this means, but my talk will be independent of hers, and I will emphasize how much number theoretic information one can squeeze out of this. Yeah. So to simplify my notation, today gamma n will be SP and Z, and I write just MNK, and gamma will be some congruence of gamma n. I hope I will stick to this notation, and I just write MNK of gamma should be MN ZK of gamma. Okay. So let me start with a general remark. So if F is a I take M here. Now M now this is in H M plus N, then I already used tacitly that this is an element of the tensor product of the spaces of modular forms for, in n and m variables. More precisely, we can write it in this way. Maybe there is an expression like this. Now this is just linear algebra. But we come into a serious problem of present-day number theory to determine these coefficients Cij in the case where capital F is a Hecke eigenform. And the Fi what is Cij? For instance, in some cases Cij can be 0. Yeah? It does not, those modular forms do not appear at all. And today I will mainly talk about the case where capital F is the simplest possible modular form, that is a Siegel-type Eisenstein series. I have to say, again, that this is a really serious present-day question of research to determine the Cij. In the first non-trivial case, that is in a degree 2, with a so-called Saito-Kurokawa lifting, where you start from an elliptic modular form and produce some cusp form of degree 2 and do this kind of restriction. 10 years ago, there was an article in Invenciones of 100 pages solving this problem. Yeah? So this is a serious problem, sometimes called branching problem for modular forms. And the only idea which one can possibly have is that these Cij will be values of L functions. Therefore, it fits also to our subject here. Pardon, monsieur. Okay, so the only chance one has usually is that these Cij will be values of L functions, sometimes outside of convergence, and sometimes one knows a priori that they will be 0. Yes, okay. And the same question you can ask not just for this restriction, but also when you use the generalization of these restrictions, that is, application of the differential operators which I mentioned before, that you differentiate first and then you restrict. And the same for differential operators d rho. Recall that this meant that you somehow differentiate these things and then you put these to be equal to 0, and then you can get something vector valued in general. Okay. So today F will always be Ziegel Eisenstein series. This is among the modular forms which I constructed last time, or maybe in my second talk, no, maybe third talk. But when I introduced it, I used some notation where these Eisenstein series fitted into a general construction, but I will use specific notation now for this case. So I call it ENK of Z. Z is in H N. But I will use it at least sometimes in a slightly more general setting with a variable s in C, and then here determinant of imaginary part of them z to the s has to be added. This was equal to m. No? And this has a meromorphic continuation to all of C as a function. So, and now let's try to look at this kind of problem. What is specific about the Eisenstein series? The Eisenstein series is not just capital F, but it has been constructed by these summation over these cosets. So this problem, yeah, E n plus m k, and we always take m is bigger or equal to n. Some cosets, suppose these coming from this kind of summation. Let us consider I could write gamma n now, gamma n plus m modulo gamma n plus n infinity. But from the right side, because we have then these variables z and w, when we understand this, then, well, by filling up these left cosets by this action of from the right here, we can separate things for the variables z and w. And now, this is an interesting question by itself. So let me first recall the simplest case. It strongly depends, everything strongly depends, of course, on the entries which you allow for the symplectic groups in question. So that is, all the entries are now in a field. Yeah? And there it's no field. Field. No number. It is really now a geometric algebra, what we get. So remember, m was bigger or equal to n, and you just get n plus 1 n plus 1 such double cosets, and I write down the some representatives and now here is a m plus n cross m plus n matrix which are no, I must write blocks. This is a slightly, this is m, this is n, and this is 0, and we have something here which is n by n, and so here some zeros are left, and the same happens here due to the symplecticity. This is transposed and still 0, and also here it's 0. Yeah. You can rephrase this in geometric terms, talking about certain isotropic subspaces, isometry classes of these. But this is basically what you can get. This is our number field. Now you know how such statements, in principle at least, transfer to the case where you have a principal ideal domain instead of a field. Somehow the elementary divisor theorem comes in. Huh? Over Z matrices, which I will call D, of size n by n, rank R. This is certainly more difficult to prove than the one above, but okay, and I call gamma D this matrix, which is so, okay. Okay, this one has to compute explicitly, and this is not so difficult. This means just to compute with some block matrix decompositions. Huh? This is a certain subgroup, and you will see why this appears. This is the sum over D, all elementary divisor matrices of size n and rank R. Lower upper divided by H. And now I prefer, instead of determinant of Cz plus D, I write the automorphic factor. We take here this gamma D times gamma z0 w to the minus k. And once you know explicitly this group H here, you are in a good situation, because then you can consider this summation for Z and W, and you will identify these modular forms with something that is known in degree n and in degree m. I will not bother you with this using explicit form of the group H, HD. Okay. In yeah, I will emphasize that there are two ways to do this. Mainly the analytic way has been done by Jolanta in the case of Jacobi forms, which is a little bit different. So I only write down the case m is equal to n, because otherwise I had to introduce Klingen-Eisenstein series with such a parameter as this I don't want to do. So now I take what is called the Petersen inner product. I never explained this explicitly, but it has appeared several times in Alexei's talk. This is bar here, and now I have a problem. I want to get something that is holomorphic in Z, so I write minus Z bar, and then at the end it will be something holomorphic. That is not, but this is not so important. And now to introduce this Petersen product, we need this will be invariant volume here. And what this gives now is the following: we get back f as a function of z, but disturbed by Hecke operators which come from these these elementary divisor matrices D. When I write this, it means up to gamma factors. Yeah? I wanted to have some S here still. So it will be something I call lambda f s of w, which means, which is defined as the following: you take the sum over all d, you take your f, you apply the Hecke operators coming from these double cosets, minus 2s minus k of z. So you get back f itself, but disturbed by infinite sum of Hecker operators. And if f is an eigenform, then the sum comes down to f times the sum of eigenvalues. Yeah? It's f times the eigenvalue for this Hecker operator. And this infinite sum is then equal to what we had called the standard L function. This is a standard L function. It has an Euler product with Euler factors of degree 2n plus 1. Well, this is not such a new story because of that. It has also appeared in a similar way in the talks of Jolanta and in the Hermitian case by Alexei. Okay, so we get back just f up to the value of a standard L function and up to some gamma factors. This identity requests some considerations about Hecker algebras by expressing this standard L function in terms of, which was done in Satake parameters. You have to express it instead in terms of double cosets to get this identity, but this can be done. So by integrating here this cusp form against the Eisenstein series of the double size, you just get back your function, but together with this L function. And this means this L function has analytic continuation because the Eisenstein series has this. Yeah, all the analytic properties of the Eisenstein series carry over to this. So this was the analytic version. This is not completely the solution of our problem because I do some integration and some things might vanish. And it's only for cusp forms because otherwise this does not converge at all. So let's look more carefully at the algebraic way where we just take s is equal to 0, but we allow n plus m instead of this. And anyway, if we allow arbitrary s, we cannot get any algebraic information out of it. This is not, with arbitrary s, it is not a holomorphic modular form here. It's just a C infinity function, the function of z and w. So there will be no direct number theory unless we restrict to s is equal to 0 or something like that. So this is 4, 1, 3. So this is due to Garrett. So we take s is equal to 0, and M can now be arbitrarily bigger than. So now I write two versions. First of all, a linear version. Linear version means I do not insist that my modular forms are eigenforms. So remember the double cosets over the field, they had n+1 representatives, just n+1. And according to that, we will have, first of all, a sum of n+1 terms. And the first term is just Eisenstein series and then we get some middle terms. So we sum over cusp forms, bases of cusp forms of degree r, and here comes something I have to explain. So this is S is equal to 0. Of z times E n r k of f j r of w. I will explain these notions m r in a moment. And now the last term runs over cusp forms of degree n. Lambda n So again, summation here is over basis. So here we produce, and this again had been in a previous lecture among the general constructions, that starting from a cusp form of degree r, I can produce a modular form of degree m by j and z to the minus k f of mz star. And star was just the upper left corner of size r, and m had to run in gamma n modulo something I had called c gamma m it's a maximal parabolic subgroup. Okay. So basically, you should keep in mind, you run over all bases of cusp forms of lower degree, and you produce these Klingen-Eisenstein series, but you also have to put in these infinite sums of Hecke operators. Yeah? And this is already a solution to the problem which I mentioned at the beginning, to describe explicitly the restriction of the Siegel-Eisenstein series to such block matrices. Yeah. And it's remarkable and not obvious from the beginning that you have the same functions here. Yeah. In my original writing with the coefficient Cij, there is no connection here. Yeah. So a lot of things which could be there are not there. Yeah. They appear here again. So this was a linear version, and it's now easy to write down a multiplicative version. That is, instead of taking any basis here, we take eigenforms, and then suddenly all these things just become multiples of these functions by the L series. Pardon?
Without multiplicity 1, how do you choose?
How do you get this? Just by the coset decomposition. This is just, you don't need any multiplicity 1.
For the basis. You use
Yeah, you use any basis.
any basis.
Any basis. Because you need what is called the reproducing formula.
Yeah, but it could be not orthogonal.
Doesn't matter. Ah, maybe orthogonal. Okay, maybe. Maybe this is better, yes. Okay. Yeah. It's orthogonal basis. Thank you. Yeah. But no Hecke eigenform up to now. But now I write down the version. And this I get from this formula just by writing the, instead of these maps, these linear maps, lambda r, I write the standard L function. So I really have to write it AMK. N minus 1, so so these values of the L functions come up. So, okay. both of these versions are quite useful, and now let's see what we can get out of this. So, for instance, this theorem that m and rho of gamma, and now gamma arbitrary, would be m and rho of gamma or z, at least bounded denominators, tensor C. That is, the full space of modular forms can be obtained by looking only at modular forms with integral Fourier coefficients or Fourier coefficients with bounded denominators. Okay, so let's look only at gamma is equal to gamma n, rho is just determinant to the k, and k is large, which I should have mentioned before, because this only works if k is bigger than m plus 1 for convergence reasons. There's a delicate problem whether this kind of thing is still true for small weight after so-called Hecke summation, but this is a different matter here in my talk. But all these conditions can be removed. So how can we get this? So this has been done. We only use for this thing, we can use a Fourier expansion just for W. Then the Fourier coefficients will be functions of Z. Right away, these are functions which are modular forms for Z, and they inherit the Fourier coefficients from the Fourier coefficients of this Eisenstein series, which we know is rational with bounded denominators. So these phi t, they are all in m n k of gamma n Z prime. No? And our claim is that these functions generate the space of modular forms linearly. course, this is an infinite set, but this does not matter. And if this is true, then we are done. Yeah? Then everything comes from the result of Siegel, that the Eisenstein series have rational Fourier coefficients with bounded denominators. So 3, 4, 5, 3, 4. Should be well, orthogonal with respect to the Petersen product extended to non-cusp forms. This is a slight cheating here. Extension cusp forms. Well, you may assume that F0 is cuspidal for simplicity, otherwise one has to use such an extension of the Petersen product. On the one side, it equals this lambda n of f, which is this infinite sum of applying Hecker operators to this. So, but since it is orthogonal to all the phi t, it is 0. No? I assume that it's orthogonal to all these. Now, on the other hand, let's see what's happening here. This is bijective. Why? It maps eigenforms on non-zero multiples of these eigenforms. Because what is happening for eigenforms, you just multiply them by this value of the L function which is different from 0. Consider Hecke eigenforms, then this lambda n 0 is just L of f k minus n times f, and this is different from 0. So then we have our claim. Oh. With a slight cheating about non-cusp forms, but this can be repaired. It's a slight cheating. Okay. Okay. So we get this theorem. I want to repeat this by using Eisenstein series of degree 2n and taking these blocks and making a Fourier expansion with respect to one of the blocks. And these Fourier coefficients are functions of the other variable, and these will generate our modular space of modular forms, and the Fourier expansion properties we get from the Fourier expansion of the Siegel-Eisenstein series. Now, this all also works if we apply these differential operators d rho, and then we get it for vector value case. Operators d rho okay. So if you go to congruent subgroups, possibly one needs integers in a cyclotomic field. So you have to take the integers in a cyclotomic field, possibly. Okay. Because the Fourier expansions of Siegel-Eisenstein series for congruent subgroups will not always be rational, but sometimes just have integral Fourier coefficients in the cyclotomic number field. Okay. And I want to remind you that from this theorem we also get that the Hecke eigenvalues will be algebraic numbers, because the Hecke operators, when properly, well, let's just go to Q here, the Hecker operators map rational modular forms with rational Fourier coefficients to modular forms with rational Fourier coefficients, and even more, if we properly normalize the Hecker operators, they keep even this space stable, and so we get that the Hecker eigenvalues will be algebraic numbers, and after proper normalization of the Hecker operators, they will be algebraic integers. Okay, and yeah, this you get from here just by the weaker statement that you have Q here instead of Z. And it's very useful to have this action. Okay. So an application of this, which has been used before also in Alexei's talk tacitly, at least for the Hermitian case, but let's see that we can see that the values of our L functions, the critical values, are algebraic. And even more, we can see, we can also squeeze this out from our formulas, that they are compatible with the action of this sigma. Yeah. I take E to N K of Z expansion. So we have first I write down just the essential parts, namely we take Fi maybe I forgot the Petersen product in the formula before, plus something forms. This is still equal to because it doesn't matter whether we apply sigma or not. Yeah, you can get this version by applying sigma to all the terms, but it's still the same as before. Still the same as before. So now let f be equal to f1, say. In two ways. We can use this formula here, then get the sum over this fi. Of I k minus n sigma fi f sigma fi sigma divided by fi sigma, but at the same time it's also equal to fi sigma k minus n f1. Yeah, because this formula holds for any eigenform, and f1 sigma is still an eigenform, and comparison gives L f1 sigma k minus n divided by what should I take here? Yes. And this gives us the algebraicity which we want. Yeah. So, okay. Now I have some time left, and I can tell a little bit about integrality properties of these L values. I just showed you that they are algebraic, but compared with values of Riemann zeta function, we do not know anything a priori about their numerator or denominators. So do denominators of these values, which we have seen to be algebraic, do they mean anything? So it is assume T minus n divided by ff now this is algebraic prime ideal p dividing p. Or assume that the eigenvalues are all rational, then we can forget about going to a prime ideal. Well, I should say that this doesn't make that much sense unless we normalize f in some way, because we coefficients of small f. The problem is we can consider this also by this quotient also for after multiplying f by a transcendental number. Yeah? And so this quotient is only algebraic if the Fourier coefficients here are algebraic. This is no contradiction to the general action of the Galois group, but we can get algebraicity of this only if f has algebraic Fourier coefficients. But to speak about the denominator, we still have to normalize f. And this is something we never talked about. I should have mentioned this right in the first lecture. It is a problem to normalize Siegel modular forms because there is no first Fourier coefficient. Yeah? Of f such that minimum so something like this, that the GCD of all the Fourier coefficients is co-prime to our prime p. Yeah? This is a kind of normalization of our modular form, and then it makes sense to talk about the prime p to appear in the denominator. Now it's a pity that my formula of Garrett is no longer there. When assume that this prime p does not appear in the denominator of the Eisenstein series. So we had the Eisenstein series being equal to some sum of these functions where also this appears on the right hand side. And on the left hand side, p does not appear in the denominator of the Eisenstein series. This by assumption. Yeah? So how can it be that on the right hand side in this finite sum of the Garrett decomposition we have summands where p appears in the denominator, but the sum is p integral? How can this happen? It can only happen because of congruences among the modular forms. Yeah? Otherwise it does not work. So this kind of denominator in other words, such a denominator, such a prime appearing in the denominator implies a congruence among modular forms. And this has been explored and very much by Katsurada and his collaborators, but not so much for the congruences among the modular forms, but the congruences among the eigenvalues. Yeah? But as I mentioned before, congruences for the Fourier expansion implies congruences for the eigenvalues. Yeah? So we get these denominators become a source of congruences. Yeah? And one can even go further, and this thing of Garrett is compatible with inserting twists by Dirichlet characters here. Yeah? And you can work with arbitrary Dirichlet characters here. And the amusing thing is there can be only finitely many congruences among modular forms, and then you will see that by varying the twist by Dirichlet characters here, you cannot get arbitrary many denominators. Yeah? So you can get a kind of Clausen von Staudt theorem for such a thing. So by varying the characters here, you cannot produce many denominators, because after all these denominators should produce congruences, and there cannot be too many congruences. Yeah? Okay, so finally, maybe I will really stop a little bit earlier then. I should. You might think you start from the Ziegler-Eisenstein series and you take arbitrary blocks, not two blocks. Then you still get something in the tensor product of the spaces of modular forms, of course. But to determine what appears there is not so easy, and in general it will not work. The only exception, except for, you take degree 3 Eisenstein series and you take here Z1, Z2, this works. Here you can do something. And here you get something that is called triple product L function. Say K prime, Fi, Gj. And you can analyze the triple L function the same way as we did before for the standard L function. But already here you see a significant difference. In our previous case, only the same Fi were appearing here. Here, these run completely independently. It's not Fi of Z times Fi of Z2 times Fi of Z3, but it's running independently. Yeah? And why does this method not work in general? In general, suppose that say SP and even over a field, say they will become too complicated. You remember in our case we had just finitely many orbits, yeah, and in general you will get infinitely many orbits, then you have no chance to get something reasonable. So this method is really limited more or less to the standard L function or to this triple product case. Maybe some more exotic cases will work, maybe with exceptional groups, but in general this is more or less the end of this kind of story. Okay, maybe you are not unhappy if I finish 5 minutes ahead of time.
Okay.
Okay, thank you.
And tell me your confidence module 23, how it appears in this setting for clean mechanisms like this.
Yeah, but this came up by really explicit computation of Fourier expansions of Klingen-Eisenstein series. Yeah. Yeah, it does not quite fit. You think maybe, but that congruence was found before the observation that it is related. That the denominators are related to congruences. Yeah, so nobody considered this. I don't know whether it's possible. Yeah, I know that you like this very much, but. That congruence was done before this observation about the denominators.
What in your PhD? What is it in your PhD thesis?
What is?
PhD thesis.
Your
PhD thesis was the congruence module 23. Was it related to your PhD thesis?
Yes, it was in my PhD thesis, yeah, in the published form, yes. But there I used kind of Cohen function, yeah, ckk minus 1. It's like these phi t's which I mentioned before, yeah. No, it was the Cohen-Eisenstein times theta, some theta series, so you get the modular form of integral weight, and this generates the full space over the Hecke algebra. And this is the same as using these phi t's which I had here. Yeah? And so this congruence mod 23 came out of an analysis of these phi t's, these Fourier expansions, partial Fourier expansions. Yeah, that was just an explicit. At that time, it came up accidentally in my thesis. Yeah, and I did not, never again looked at the question whether it comes really from such a denominator. Yeah. So, thank you.